Plug-in hybrid electric vehicles, PHEVs, use batteries to power an electric motor, as well as another fuel, such as gasoline or diesel, to power an internal combustion engine or other propulsion source. PHEVs can charge their batteries through charging equipment and regenerative braking. Using electricity from the grid to run the vehicle some or all of the time reduces operating costs and fuel use, relative to conventional vehicles. PHEVs may also produce lower levels of emissions, depending on the electricity source and how often the vehicle is operated in all-electric mode. There are several light-duty PHEVs commercially available, and medium-duty vehicles are now entering the market. Medium and heavy-duty vehicles can also be converted to PHEVs. Although PHEVs are generally more expensive than similar conventional and hybrid vehicles, some cost can be recovered through fuel savings, a federal tax credit, or state incentives. PHEVs have an internal combustion engine and an electric motor, which uses energy stored in batteries. PHEVs generally have larger battery packs than hybrid electric vehicles. This makes it possible to drive moderate distances using just electricity, about 15 to 60 plus miles in current models, commonly referred to as the electric range of the vehicle. During urban driving, most of a PHEV's power can come from stored electricity. For example, a light-duty PHEV driver might drive to and from work on all-electric power, plug the vehicle in to charge at night, and be ready for another all-electric commute the next day. The internal combustion engine powers the vehicle when the battery is mostly depleted, during rapid acceleration, or when intensive heating or air conditioning loads are present. Some heavy-duty PHEVs work the opposite way, with the internal combustion engine used for driving to and from a job site and electricity used to power the vehicle's auxiliary equipment or control the cab's climate while at the job site. PHEV batteries can be charged by an outside electric power source, by the internal combustion engine, or through regenerative braking. During braking, the electric motor acts as a generator, using the energy to charge the battery, thereby recapturing energy that would have been lost. Learn more about charging PHEVs. PHEV fuel consumption depends on the distance driven between battery charges. For example, if the vehicle is never plugged in to charge, fuel economy will be about the same as a similarly sized hybrid electric vehicle. If the vehicle is driven a shorter distance than its all-electric range and plugged in to charge between trips, it may be possible to use only electric power. Therefore, consistently charging the vehicle is the best way to maximize the electric benefits. Beyond battery storage and motor power, there are various ways to combine the power from the electric motor and the engine. The two main configurations are parallel and series. Some PHEVs use transmissions that allow them to operate in either parallel or series configurations, switching between the two based on the drive profile. Parallel hybrid operation connects the engine and the electric motor to the wheels through mechanical coupling. Both the electric motor and the engine can drive the wheels directly. Series plug-in hybrids use only the electric motor to drive the wheels. The internal combustion engine is used to generate electricity for the motor. Vehicles of this type are often referred to as extended-range electric vehicles. The electric motor drives the wheels almost all of the time, but the vehicle can switch to work like a parallel hybrid at highway speeds when the battery is depleted. A plug-in hybrid electric vehicle, PHEV, is a hybrid electric vehicle whose battery pack can be recharged by plugging a charging cable into an external electric power source, in addition to internally by its onboard internal combustion engine-powered generator. Most PHEVs are passenger cars, but there are also PHEV versions of sports cars, commercial vehicles, vans, utility trucks, buses, trains, motorcycles, mopeds, military vehicles and boats. Similar to all electric vehicles, BEVs, PHEVs displace greenhouse gas emissions from the car tailpipe exhaust to the power station generators powering the electricity grid. These centralized generators may be of renewable energy, e.g. solar, wind or hydroelectric, and largely emission-free, or have an overall lower emission intensity than individual internal combustion engines. Compared to conventional hybrid electric vehicles, HEVs, PHEVs have a larger battery pack that can be charged from the power grid, which is also more efficient and can cost less than using only the onboard generator, and also often have a more powerful electric output capable of longer and more frequent EV mode driving, helping to reduce operating costs. A PHEV's battery pack is smaller than all electric vehicles for the same vehicle weight, due to the necessity to still accommodate its combustion engine and hybrid drivetrain, but has the auxiliary option of switching back to using its gasoline/diesel engine like a conventional HEV if the battery runs low, alleviating range anxiety especially for places that lack sufficient charging infrastructure. Mass-produced PHEVs have been available to the public in China and the United States since 2010, with the introduction of the Chevrolet Volt, which was the best-selling PHEV until the end of production in 2019. Citation needed: by the end of 2017, there were over 40 models of Highway Legal Series production PHEVs for retail sales, and are available mainly in China, Japan, the United States, Canada, and Western Europe. The top-selling models are the Mitsubishi Outlander PHEV, the Chevrolet Volt family and the Toyota Prius PHEV. As of December 2019, the global stock of PHEVs totaled 2.4 million units, representing one-third of the stock of plug-in electric passenger cars on the world's roads. As of December 2019, China had the world's largest stock of PHEVs with 767,900 units, followed by the United States with 567,740, and the United Kingdom with 159,910. A plug-in hybrid's all-electric range is designated by PHEV-miles or PHEV kilometers km, in which the number represents the distance the vehicle can travel on battery power alone. For example, a PHEV 20 can travel 32 kilometers, 20 miles, without using its combustion engine, so it may also be designated as a PHEV 32 km. For these cars to be battery operated, they go through charging processes that use different currents. These currents are known as alternating current, AC, used for onboard chargers, and direct current, DC, used for external charging. Other popular terms sometimes used for plug-in hybrids are grid-connected hybrids, gas-optional hybrid electric vehicle, GO-HEV, or simply gas-optional hybrids. GM calls its Chevrolet Volt series plug-in hybrid an extended-range electric vehicle. The Loner, Porsche mixed hybrid, produced as early as 1899, was the first hybrid electric car. Early hybrids could be charged from an external source before operation. However, the term plug-in hybrid has come to mean a hybrid vehicle that can be charged from a standard electrical wall socket. The term plug-in hybrid electric vehicle was coined by UC Davis professor Andrew Frank, who has been called the father of the modern plug-in hybrid. The July 1969 issue of Popular Science featured an article on the General Motors XP883 plug-in hybrid. The concept commuter vehicle housed 6 12-volt lead-acid batteries in the trunk area and a transverse-mounted DC electric motor turning a front-wheel drive. The car could be plugged into a standard North American 120-volt AC outlet for recharging. PHEVs are based on the same three basic powertrain architectures of conventional hybrids. A series hybrid is propelled by electric motors only, a parallel hybrid is propelled both by its internal combustion engine and by electric motors operating concurrently, and a series parallel hybrid operates in either mode. While a plain hybrid vehicle charges its battery from its engine only, a plug-in hybrid can obtain a significant amount of the energy required to recharge its battery from external sources. The battery charger can be onboard or external to the vehicle. The process for an onboard charger is best explained as AC power being converted into DC power, resulting in the battery being charged. Onboard chargers are limited in capacity by their weight and size, and by the limited capacity of general-purpose AC outlets. Dedicated off-board chargers can be as large and powerful as the user can afford, but require returning to the charger. High-speed chargers may be shared by multiple vehicles. Using the electric motor's inverter allows the motor windings to act as the transformer coils, and the existing high-power inverter as the AC to DC charger. As these components are already required on the car, and are designed to handle any practical power capability, they can be used to create a very powerful form of onboard charger with no significant additional weight or size. AC propulsion uses this charging method, referred to as reductive charging. A plug-in hybrid operates in charge-depleting and charge-sustaining modes. Combinations of these two modes are termed blended mode or mixed mode. These vehicles can be designed to drive for an extended range in all-electric mode, either at low speeds only or at all speeds. These modes manage the vehicle's battery discharge strategy, and their use has a direct effect on the size and type of battery required. Charge-depleting mode allows a fully charged PHEV to operate exclusively, or depending on the vehicle, almost exclusively, except during hard acceleration, on electric power until its battery state of charge is depleted to a predetermined level, at which time the vehicle's internal combustion engine or fuel cell will be engaged. This period is the vehicle's all-electric range. This is the only mode that a battery electric vehicle can operate in, hence their limited range. Mixed mode describes a trip using a combination of multiple modes. For example, a car may begin a trip in low-speed charge-depleting mode, then enter onto a freeway and operate in blended mode. The driver might exit the freeway and drive without the internal combustion engine until all electric range is exhausted. The vehicle can revert to a charge-sustaining mode until the final destination is reached. This contrasts with a charge-depleting trip which would be driven within the limits of a PHEV's all-electric range. Most PHEVs also have two additional charge-sustaining modes. Battery hold: the electric motor is locked out and the vehicle operates exclusively on combustion power, so that whatever charge is left in the battery remains for when mixed mode or full electric operation are re-engaged, whilst regenerative braking will still be available to boost the battery charge. On some PHEVs, vehicle services which use the traction battery, such as heating and air conditioning, are placed in a low power consumption mode to further conserve the remaining battery charge. The lockout of the electric motor is automatically overridden, charge permitting, should full acceleration be required. Self-charge: the electric motor's armature is engaged to the transmission, but is connected to the battery so that it runs as a generator and therefore recharges the battery whilst the car is in motion, although this comes at the expense of higher fuel consumption, as the combustion engine has to both power the vehicle itself and charge the battery. This is useful for charging on the move when there are limited places to plug the vehicle in. The optimum battery size varies depending on whether the aim is to reduce fuel consumption, running costs, or emissions, but a 2009 study concluded that the best choice of PHEV battery capacity depends critically on the distance that the vehicle will be driven between charges. Our results suggest that for urban driving conditions and frequent charges every 10 miles or less, a low-capacity PHEV sized with an all-electric range of about 7 miles would be a robust choice for minimizing gasoline consumption, cost, and greenhouse gas emissions. For less frequent charging, every 20 to 100 miles, PHEVs release fewer GHGs, but HEVs are more cost-effective. PHEVs typically require deeper battery charging and discharging cycles than conventional hybrids. Because the number of full cycles influences battery life, this may be less than in traditional HEVs which do not deplete their batteries as fully. However, some authors argue that PHEVs will soon become standard in the automobile industry. Design issues and trade-offs against battery life, capacity, heat dissipation, weight, costs, and safety need to be solved. Advanced battery technology is under development, promising greater energy densities by both mass and volume, and battery life expectancy is expected to increase. The cathodes of some early 2007 lithium-ion batteries are made from lithium cobalt metal oxide. This material is expensive, and cells made with it can release oxygen if overcharged. If the cobalt is replaced with iron phosphates, the cells will not burn or release oxygen under any charge. At early 2007 gasoline and electricity prices, the break-even point is reached after 6 to 10 years of operation. The payback period may be longer for plug-in hybrids, because of their larger, more expensive batteries. Nickel, metal hydride and lithium-ion batteries can be recycled. Toyota, for example, has a recycling program in place under which dealers are paid a $200 credit for each battery returned. However, plug-in hybrids typically use larger battery packs than comparable conventional hybrids, and thus require more resources. Pacific Gas and Electric Company, PG&E, has suggested that utilities could purchase used batteries for backup and load leveling purposes. They state that while these used batteries may be no longer usable in vehicles, their residual capacity still has significant value. More recently, General Motors, GM, has said it has been approached by utilities interested in using recycled volt batteries as a power storage system, a secondary market that could bring down the cost of the Volt and other plug-in vehicles for consumers. Ultracapacitors, or supercapacitors, are used in some plug-in hybrids, such as AFS Trinity's concept prototype, to store rapidly available energy with their high power density, in order to keep batteries within safe resistive heating limits and extend battery life. The Xero's Ultra battery combines a supercapacitor and a lead-acid battery in a single unit, creating a hybrid car battery that lasts longer, costs less and is more powerful than current technologies used in plug-in hybrid electric vehicles, PHEVs. There are several companies that are converting fossil fuel non-hybrid vehicles to plug-in hybrids. Aftermarket conversion of an existing production hybrid to a plug-in hybrid typically involves increasing the capacity of the vehicle's battery pack and adding an onboard AC to DC charger. Ideally, the vehicle's powertrain software would be reprogrammed to make full use of the battery pack's additional energy storage capacity and power output. Many early plug-in hybrid electric vehicle conversions have been based on the Toyota Prius. Some of the systems have involved replacement of the vehicle's original NIMH battery pack and its electronic control unit. Others add an additional battery back onto the original battery pack. Advantages of plug-in hybrid cars. The primary advantage of a PHEV is that it offers the low running costs, low emissions, and possible tax incentives of an electric vehicle without the range anxiety. With a plug-in hybrid, you might be able to commute and run your daily errands without ever using the gas motor, and because of the backup gas-powered engine, you won't have to worry about getting stranded without a charge on long trips. Disadvantages of plug-in hybrid cars. Disadvantages of the plug-in hybrid vehicle include its heavy battery, which can cause it to get worse mileage compared to a non-hybrid vehicle when running exclusively on the combustion engine. The battery packs are expensive, too. PHEVs usually cost more upfront than either a traditional hybrid or a gas-only vehicle. If you want to make the most of your PHEV, you'll want to install a 240V outlet or charging station at your house, which can also be costly. Thank you for watching this video.